Almost done grading your tests. I'm hoping I can be done today. Can't guarantee it, but I'm hoping so. I just have the proofs left to grade. So I'll give it my best shot. Hopefully get it done today. Next week, I have to be gone Wednesday and Friday, so you only have class in here Monday of next week. Wow, like an extra long break from algebraic structures. Well, that does mean you could forget a lot, right? Then so we'd have class next Monday, and then you wouldn't have class for 2 more weeks till the Monday after spring break. You could forget a lot. So probably would be good to still study more beyond just coming to class next Monday. Continue reading, continue thinking, okay? So you'll have time to do that. Future classes, I can guarantee that I'll be gone right before spring break. So for you guys, I do. But I am actually going to try to make those days up a little bit. I'm probably going to make a video without having class meet. Maybe sometime like the Thursday before Easter, I might make an extra video. And or maybe on advising day, which is like Wednesday, April 11th or something like that. Does that sound right? I think it's the 11th of April, advising day. All right, so no quiz today, a little break from quizzes. We will have a quiz next Monday. We will have a quiz even when we come back from spring break. I think that would be good to motivate you to try to get back in the right mode of thinking about things. So we'll just have one lecture today, lecture 13. Not going to split it into 2 parts. I think I will try to give you a little treat, and hopefully we can end a little early. Okay. I want to talk a little bit more about cyclic groups and groups of permutations. We've thought about orders of elements in S4 and A4. Now today we'll think about S5 and A5 for the groups of permutations. We'll get into a lot of depth about isomorphisms and their properties. That'll be the main thing we focus on, is isomorphisms and their properties. I will briefly talk about something else in the reading automorphisms, inner automorphisms. We'll spend more time with those on Monday. I want to introduce you to Lagrange's theorem from chapter 7. You might call Lagrange's theorem the fundamental theorem of group theory. It's the cornerstone of a lot of advanced group theory. So introduction to it today, and then a lot more depth on it on Monday, as well as, again, the automorphisms and inner automorphisms. You know, I mentioned, maybe, I don't know, 2 or 3 weeks ago, that when you first start learning about cyclic groups, they seem pretty difficult, I think, at first. But then once you're through later in the class, you look back on cyclic groups and say that's the easy stuff. Maybe you're even at that point right now, maybe. It's good to try to visualize cyclic groups too. We really haven't done that beyond making Cayley tables. One way to visualize them is as subgroups of, what did C star represent? Set of complex numbers without the number 0. What was the operation that made this a group? Multiplication, not addition. And you don't want 0 in there, okay? S1 is the unit circle thought of as a subset of the complex plane. That's a group as well. And I haven't really talked about that a ton in class. I briefly mentioned it. It is in the book in chapter 0, if you're interested in learning about that more. But you can visualize finite cyclic groups, or in fact even infinite cyclic groups, as subgroups of both of these groups. And you can do it on Mathematica, and I'm going to show you. Here's a screenshot of what I'm about to show you in Mathematica. So this would be the unit circle, this blue circle here in the complex plane, labeled with a real axis and imaginary axis. But that axis is there, I see it. Okay, it is there. And what we have here is a visual of the cyclic group of order 5. You see 1, 2, 3, 4, 5 elements. This is the number 1. It's the identity in this group. I'm calling this element omega squared. Evidently this point right there would be omega. What would omega be? Again, you can find this in chapter 0. You can use essentially polar coordinates to represent omega. You can write it as, well, we got to go 1/5 of a turn around the circle. So take going the entire way around the circle would be 2 pi radians of an angle. So this would be 2 pi over 5 radians. This is called a primitive, in this case, 5th root of unity. Unity standing for the number 1. A primitive 5th root of unity, and it is a generator for the cyclic group that you see visualized here. Every time you multiply an element by omega, you shift, you rotate, so to speak, by the angle 2 pi over 5 in radians from here to here when you multiply by omega. Then you multiply by omega again, you're going to get this point, omega cubed. Then omega to the 4th, then omega to the 5th brings you back to the identity. This is a cyclic group. Then you can keep going, omega to the 6th, omega to the 7th, and then you can mod the power. Omega to the 7th, for example, is omega squared. And you can rotate backwards. The inverse of omega is down there. That's omega inverse. Omega to the negative 1 power. This is omega to the negative 2 power. Omega to the negative 3 is the same as omega squared. The powers differ by a multiple of 5. Omega to the negative 4, omega to the negative 5 brings you back to the identity. I did actually put this code in our folder, our shared folder. So I was working on this yesterday, and this is the code that sort of leads up to the final animation. So you can see it's fairly complicated looking code, but it does give us kind of a nice final animation. And I have set
it's not on the screen.
I could.
It's not on the screen.
Oh, okay, that's good. Okay, thanks. Somehow I got in this presenter mode in PowerPoint, and I don't know how. Okay, now why is not Mathematica not showing? It's on my screen. Ah.
Drag it over.
Is it in the wrong spot? Oh, there we go. And I know how to actually drag it over. Okay, let me just do this. Let me try to look up there. Make it smaller too. I don't know how this computer got in this mode. Can I see the mouse over there? Okay, so I can change n. I could change n from 5 to 6, for example. 7, 8, 9, 10. There's a cyclic group of order 10, and I can keep increasing the power of omega. Go from omega to omega squared to omega cubed, etc. And you're cycling. It's a cyclic group. And I can go backwards, essentially multiplying by the inverse of omega, and I do set it up to get negative powers there. Okay, so it's a nice way to visualize cyclic groups. And what this is also illustrating, pretty amazingly if you think about it, this group, well, the blue circle, S1, is a group under multiplication. It's an infinite group. It's not cyclic, but it's got infinitely many different cyclic groups of every single order, including infinite order too, although I haven't verified that. It's got a cyclic group of order 1, subgroup of order 1, just 1 by itself. It's got a cyclic subgroup of order 2, 1 and negative 1 by themselves. It's got a cyclic subgroup of, for example, order 4, 1, I, that's the imaginary unit I up there, then negative 1, then negative I, form a cyclic subgroup of order 4. Here's your cyclic subgroup of order 10. The unit circle, thought of as a group under multiplication in the complex plane, has subgroups of every finite order. Finite cyclic subgroups of every finite order. And it's also got infinite cyclic subgroups as well. If my angle here was not a rational multiple of pi, then actually it would not cycle back to itself. I'd get an infinite cyclic subgroup, isomorphic to z instead of zn. It's a pretty amazing thing, I think. All right, now let's see if I can move this back so I can see it on my screen here. And let's go back to the PowerPoint and see if that shows up. Oh, there we go. Okay. So again, I saved that in the folder, and I would encourage you to look at it and think about it. Okay. If you think about cyclic groups visually, I think it's easier than thinking about them symbolically sometimes. Doing proofs with cyclic groups is definitely a step up in difficulty, but thinking about them intuitively and visually, I think, is a good thing. Here I spent some time also thinking about S5 and A5, like I mentioned I would do. So I made one of these tables. To think about the number of elements of various orders in both S5 and A5. These are orders of elements, not orders of subgroups. There are bigger subgroups than 6, order 6. But what this is illustrating, and if you think about it further, the highest order for an element in S5 is going to be 6. Of course, it's only the identity that has order 1, and there's just one of those in S5, and it's the same thing as in A5. How many elements have order 2? Claim it's 25 in S5 and 15 in A5, and hopefully this makes sense to you. You can draw this kind of thing, for example. There's your arbitrary 2-cycle transposition. How many possible 2 cycles are there in S5? Well, you've got 5 choices for A and 4 choices for B. But remember, AB is the same as BA, so I have to divide by 2. There are 10 possible 2 cycles in S5. All of which are odd permutations, not even, right? There's just one element there, one cycle, one 2 cycle. It's an odd permutation. It's in S5, but it's not an A5. You see there's no 5 times 4 divided by 2 over there. But you can also generate elements of order 2 by composing 2 2 cycles, disjoint, say. These are going to have order 2 as well, and you'd have 5 choices for A, 4 choices for B, 3 choices for C, and 2 for D. However, you've got to divide by certain things. You've got to divide by 2 because you have, again, 2 ways to write this first permutation, AB or BA. You should also divide by another 2 because you have 2 ways of writing that permutation. And you should also divide by 2 again because these are disjoint cycles that commute. I could have also written it this way. And so if you don't divide by 2 again, you'd be counting each element twice. Altogether giving you 15 elements of order 2 of this form in S5. These are also in A5. These are even permutations because it's probably an even number of 2 cycles. 15 there also comes in there. I am doing these cumulative totals. And you know the order of S5 is 5 factorial 120. I'm supposed to get 120 at the end. And the order of A5, the alternating group of degree 5, is 5 factorial over 2, 60. So I'm keeping track of the cumulative to help as a check to make sure I really got this right. For 3 cycles, A, B, C, 5 choices for the first one, 4 for the next, 3 for the next, but each of those can be written in 3 different ways, so I have to divide by 3. And there's 20 of those totally. There. 3 cycles are even. This can be written as a product of two transpositions like this, with that trick. Not disjoint, but they are two cycles. An even number of 2 cycles. 3 cycles are actually even permutations. So they are also in A5. 20 there. 4 cycles are the only way to get an element of order 4 in S5. If we were up to S6, there would be another way to get an element of order 4. And that would be to compose a 4 cycle with a disjoint 2 cycle. But you need 6 distinct objects to permute in order to be in S6. In S5, we only have 5. So it's good enough just to think about 4 cycles for elements of order 4. 4 cycles are odd permutations, actually. Again, by the trick, you can see that this is a product of 3 2 cycles. So you see a 0 there. They're not in A5, but they are in S5. And there's 5 times 4 times 3 times 2 divided by 4, because there's 4 different ways of writing that. And so that's going to be 30. Mention the 30 here, up to 76 elements total. 5 cycles are the only ways of getting elements of order 5 in S5. Number of different 5 cycles by analogous logic is this, which is 24. We're up to 100. 5 cycles are even permutations, so those 24 are also in A5. Finally, elements of order 6 in S5 are obtained by composing disjoint 2 and 3 cycles. How many of those? There's 5 times 4 times 3 times 2 times 1. Divide by 2 for the 2 different ways of writing this one. Divide by 3 for the 2 different ways of writing this one. And you don't have to think about switching these around, because it's not like you're going to get a repeat of something if you switch them around. They do commute because they're disjoint. But you know, when we were thinking about composing 2 cycles and saying these 2 things are the same, I was double counting in my products if I thought of these as being different, but they're actually the same. Here, if you switch them around, they're different lengths. And so you don't have to divide by 2 again. Giving you 20 elements of order 6 that are odd permutations. This is a composition of an odd with an even. It's got to be odd. It's the same as A, B, C, E, C, D. An odd number of 2 cycles. So those are not in A5. Double check my arithmetic. Do the cumulative totals make sense? I think so. So these again are elements of these orders, which would generate cyclic subgroups of these orders. And you could figure out the number of cyclic subgroups of the various orders. Elements of order 2, each individual element of order 2 generates a unique cyclic subgroup of order 2, so there would be 26 cyclic subgroups of order 2 in S5. I don't think you want to make the lattice, right? This would be really messy. 16 subgroups, cyclic subgroups of order 2 in A5. For elements of order 3, they come in pairs, right? Got an element of order 3A, call it A squared, is also going to have an order 3 and be in the same cyclic subgroup generated by that element of order 3. So you got to divide this number by 2. There's 20 elements of order 3. There would be 10 cyclic subgroups of order 3 in both S5 and A5. Elements of order 4 generate cyclic subgroups of order 4. There's always 2 generators of cyclic groups of order 4, right? A and A cubed, if A has order 4. So you got to divide that by 2 to say there's 15 cyclic subgroups of order 4 in S5 and none in A5. S5, or cyclic subgroups of order 5, The generators come in how many? I'm giving you a big hint here with my hand by accident. Guess it's subconscious. 4, yeah. If A has order 5, then the cyclic subgroup generated by A, all the non-identity elements, A squared, A cubed, A to the 4th, are all generators. 5 is prime. So you're going to divide that by 4 to get 6 cyclic subgroups of order 5 in both S5 and A5. And cyclic subgroups of order 6, cyclic groups of order 6 have 2 generators, A and A to the 5th. Powers that are relatively prime to 6. So you got to divide that by 2. There's going to be 10 cyclic subgroups of order 6 in S5 and none in A5. But again, that's not all the subgroups. There are some non-cyclic subgroups. In particular, well, A5 is a non-cyclic subgroup of S5. It's the most famous one to think about. And you're going to be able to find cyclic subgroups isomorphic to, for example, D3 and D4 and D5 dihedral groups. Okay, if you look for elements of the right order. I won't go into detail. I didn't really give you problems like this on that exam on, oh, what is today? Today's Friday. The exam on Wednesday? Exam on Wednesday, right? Yeah, okay. I'm already forgetting. But I could possibly give you problems related to this kind of thing on the second exam. Not the entire table, that would be too much, but maybe a piece of it. Our quizzes and exams are all going to be cumulative, because that's the best way to remember things. Though I will treat earlier things lightly on future exams, and I'll probably say what to focus on from earlier material. Okay, so I'm not going to leave you completely in the cold as far as not knowing exactly what would be on the exam from earlier material. But I think it would be good to review earlier material, because that's how you remember it better. You'll remember it better if it's consistently on your mind. All right, now on to isomorphisms again. This next slide, you don't need to write down, because you've probably written it down already. It's just the definition of an isomorphism again. An isomorphism from a group G to a group G bar, and again, every time I redo it, I copy it from my computer onto the network drive, and this gets to the wrong spot. And this G bar should be up there. There's a one-to-one mapping from G onto G bar that is operation preserving. One-to-one and onto an operation preserving, and here's the key equation as you know, and I tested you on that. Once more for emphasis, on the left-hand side, the group operation is A times B, it's in G. And on the right-hand side, the group operation is phi of A times phi of B, it's in G bar. Different groups, different operations. One of the operations could be addition and the other multiplication. I've quizzed you on that kind of thing before. Here's your generic operation preserving equation. In the abstract, we assume multiplication. In such situations, we say G and G bar are isomorphic, and we write, our book writes this, and I will try to stay consistent with our book. But don't say approximately equal to, say isomorphic to. They are, in general, different groups. For example, S3 and D3 are different groups. They do share a commonality in the elements being functions and the operation being function composition, but they are defined differently. That's symmetries of an equilateral triangle. That's permutations, all permutations on the set of 3 objects, 1, 2, 3. So they are different groups, but they are isomorphic. They act the same. I'm going to show you an example of an isomorphism between these here in a minute. Okay? You will see people write the isomorphism symbol in different ways. But this is what our textbook does, and I will stay consistent with that. Here are some specific isomorphisms. For a group element A that has infinite order, the cyclic group generated by A is going to be isomorphic to Z. All cyclic groups of infinite order are isomorphic to Z. Z, in a sense, is your prototype, though it's sometimes easier to think about the abstract case as being a prototype. Here the operation is multiplication, we're talking abstract. Here we're talking specific, and the operation is addition. The isomorphism is given by that formula. Take your general element of the cyclic subgroup generated by A, where K is an integer power, could be negative as well. In general, it will be negative. If A has infinite order, it will be, or it could be. You map A to the K to K. Why is this an isomorphism? Is it one-to-one if phi A to the K equals phi of A to the M? That implies A to the K equals A to the M. And we know from that very first theorem in chapter 4, the criterion for A to the I to equal A to the J, that when A has infinite order, this means K must equal A. And therefore, A to the K equals... Wait, what am I doing? I guess I didn't need to do that. Right? Okay. Yeah. And actually, my work is with that here. I got confused. This implies K equals M, which implies A to the K equals A to the M. If the outputs are the same, the inputs are the same. That's what it should have done. Is it onto? Sure. Given an arbitrary K and Z, A to the K maps to it. Is it operation preserving? Phi of A to the K times A to the M by properties of exponent is phi to the A of A to the K plus M, which by definition of phi is K plus M, which is going to be the same as phi of A to the K plus phi of A to the M, which is the thing that you need to verify for operation preserving in this case, with a plus sign. Because the operation in GUR is the operation in Z is addition. So that verifies operation preserving. And it's got an inverse function that's also an isomorphism. Map K to K, A to the K. If A has finite order, the same formula still works, except your target, your codomain, is now Zn instead of Z. But the same formula does work. When I say K mod n there, I'm sort of imagining K could be any integer, but remember with finite cyclic groups, really it repeats. And I really didn't have to put the mod in because of that. If I think of the elements just as being these n elements and not thinking about higher powers because those give me the same elements over again, like we saw with the visualization, then I really don't have to say mod n here. K automatically would be between 0 and n minus 1. But it's one-to-one. Again, if K is thought to be between 0 and n minus 1, it's one-to-one for the same reason as you see here. If you imagine allowing K to be bigger than n, bigger than or equal to n or less than 0, then technically K and M would be equal mod n. K mod n would be equal to M mod n. But that would mean A to the K equals A to the M. In a cyclic subgroup of order n. Claim this is an isomorphism from D3 to S3. It's probably worth double checking at least one operation preserving property there. So no formula there, so to speak. I'm just saying what everything gets mapped to. R0, the identity in D3, should get mapped to the identity in S3, the identity permutation. That maps everything to itself. R120 and R240 have order 3 in D3. They better get mapped to elements of order 3 in S3. They better get mapped to 3 cycles, and so I did so. D, D prime, and V all have order 2. Those are the reflections. They better get mapped to elements of order 2. I'm hinting at a property of isomorphisms here. The order of the input has to match the order of the output, which is something you should have read about. In fact, I even said it could have shown up in the exam. What should we verify here? Maybe verify that phi of d time, or composed of d prime, is phi of d composed of phi of d prime. Is that true? I could color the vertices here. I guess I could number them as well. D was a reflection across that line of symmetry, and d prime was a reflection across that one. And I could maybe even try to make the numbers match up with what you see here as far as the image goes. It's phi of d is a permutation that swaps 1 and 2 but leaves 3 fixed. Just like d swaps these 2 vertices but leaves that one fixed. Swapping 1 and 2 but leaving 3 fixed. D prime gets mapped to a permutation that swaps 1 and 3 but leaves 2 fixed. Is that doing this visually? It's a reflection across that line. It is swapping 1 and 3 but leaving 2 fixed. What is D composed with D prime going to be? It's going to be a rotation. Right? Composed 2 reflections, you're going to get a rotation. Let's imagine doing it here. We apply D prime first. We'll swap the 1 and the 3. And then we apply D to that. We're going to swap here the 2 and the 3. As far as a counterclockwise rotation, from here to there, it's a counterclockwise rotation by 240 degrees. This is R240. So phi of D prime is the same as phi of R240. R240 is getting mapped to 1, 3, 2. Hopefully. I did check one example out before class, so hopefully this is not a problem. Hopefully this ends up being the same thing. D gets mapped to 1, 2. D prime gets mapped, you see, to 1, 3. And yes, this does, when you compose these permutations, equal the same thing. That's verifying the operation preserving property for that example. Technically speaking, you need to do it for every possible combination. I would never make you do that. Okay? That's verifying operation preserving in one instance. Lots of properties of isomorphisms acting on group elements. The identity always gets mapped to the identity. Phi of E should be the identity in G bar. How would you verify that? Well, you could imagine multiplying it times any element in G bar. And I really could pick an arbitrary element of G bar. But I also could pick a specific element of G bar. How about phi of E again? if phi of e really is the identity of G bar, then this product should also equal phi of e, right? If this really is the identity in G bar, this should also equal phi of e. Well, okay, that's probably not, that's actually not a good enough argument, because that could just verify that the square of an element is itself, and that doesn't mean the element is the identity. I guess I should take an arbitrary element of G bar. Since phi is onto and one-to-one, there's a unique element of G that gets mapped to G bar. Call it G. Since phi is one-to-one and onto. Technically, you should say because it's onto first, and then because it's one-to-one. The one-to-one means that the G is unique. So it's actually enough to say phi is onto. Let me just go ahead and say that. We will use the fact that phi is one-to-one in a second here. Since phi is operation preserving, phi is OP, operation preserving. We can say this is true. Since E is the identity of G, I can say this is true. E is identity of G. And now since phi is one-to-one, this is the same as G bar. And that does it. I've shown that an arbitrary element of G bar multiplied by phi of E is equal to G bar. You can verify it the other direction around as well. Therefore, phi of E is the identity of G bar, call it E bar. Okay? The identity gets mapped to the identity. How about the power of an element? This was on the exam. Apply phi to an arbitrary power of an element. You get the image of that element raised to the same power. By the way, you should learn how to speak what I just said there. You should learn how to say these equations in words. If you apply phi to an arbitrary power of an arbitrary element, you get the image of that element to the same power. That's how you verbalize what this equation is saying. Phi of A is the image of A. It's the value or output of A under phi, but I will often say image. Prove this for n greater than 0 on the exam with induction. Essentially, the inductive step, you first do this, then use your inductive, well, okay, use the fact that phi is operation preserving to say this. I don't have to write that first power, but I am for emphasis. Phi is operation preserving. Then use your inductive hypothesis to say phi of A to the n is phi of A to the n power. I can also write that. Now I can put the 1 up there. And now I can add those exponents. Use a property of exponents to say this. And then apply the principle of mathematical induction to say then that this is true for all positive integers n. What about when n is negative? I don't want to do a full proof, but let's consider the case when n is -1. Why is phi of the inverse of A equal to the inverse of phi of A? What I just said there. Why is the image of the inverse of A equal to the inverse of the image of A? That's another way to say it. Evidently, if I multiply this thing by phi of A, I should get the identity in G. It wouldn't matter which order you do it in. Use the fact that phi is operation preserving, and use the fact that phi maps the identity to the identity. And this fact, along with the same fact you get when you switch the order of these two things, would imply that this is true. These are all proofs that could show up on exam 2, I think. Values on commuting elements. What do you think I mean by that? If the inputs commute, then what? Yeah, then so do the outputs. Suppose A and B commute. AB equals BA. Consider phi of A times phi of B. The fact that phi is operation preserving allows you to write this. The fact that A and B commute allows you to write this. The fact that phi is operation preserving allows you to write this. Done. Operation preserving. Assumption that A and B commute. Operation preserving. A and B are arbitrary elements of G that commute. Therefore, their images, and their images also commute. The outputs, values, images of commuting elements also commute. Values on generators of cyclic groups. Well, essentially, that's the fact. Okay, it's stated differently in the book. It preserves the orders of elements. Isomorphisms preserve orders. The book did label it as a different thing as well. Suppose G itself happened to be cyclic. Then G bar is going to be cyclic as well. But these are very much related. So A is a generator of G. Y is phi of A generator of G bar. Let's just do one direction there. Give me an arbitrary element of G bar, little g bar. Why is it a power of phi of A? That's the question. The fact that phi is onto would imply there exists a little g in capital G such that phi of little g equals G bar. Right? Phi is onto, so every thing in G bar is the output, the image of something in G. G, without the bar, little g, is in capital G, which is generated by A. Little g must be a power of A. The fact that capital G is generated by A now implies that there exists an integer n such that little g equals A to the n. This is what I call follow your nose proof. You just do the only next thing you can do. And you're kind of just hoping it's going to work out, and it oftentimes does. What's the next thing you can do? I guess use operation preserving. It must be important. G bar is phi of G, which is phi of A to the n, which is phi of A to the n. That verifies that G bar is generated by phi of A, because I've taken an arbitrary element of G bar and show it's a power of phi of A. That does it. That verifies this is true. If you want to get nitpicky about it, technically I've only verified this inclusion, but the other inclusion is trivial. Phi of A is in G bar, so the cyclic subgroup generated by phi of A is automatically in G bar as well. They are equal. I didn't assume what the order of A was, whether it was finite or infinite. This proof works whether the order of A is finite or infinite. I guess the preservation of the orders property is a little different. You are focused on the definition of order. Suppose that A has order n. Why does that mean phi of A also has order n? Certainly if you raise them to the n power, you get the identity, but why does raising phi of A to some smaller power not give you the identity? Right, for the order of an element, it's the smallest positive integer power that gets you back to the identity, if there is such a power. In the finite case, that's what I'm assuming here. Suppose K is between 0 and n. Y is phi of A to the K not equal to the identity in G bar. Is the thing we really need to answer. Certainly raising it to the n power will get you back to the identity. That really should be verified, but it's pretty easy. But why do you not get back to the identity for some smaller positive power? Well, A to that positive power is not going to be the identity in G, because A has order n. And phi is 1 to 1. Distinct inputs are going to give you distinct outputs. Phi of A to the K is not going to equal phi of E, which is E bar. And this thing, by operation preserving properties that we've already mentioned, is the same as that. I'll put this back up here again in a second, but let's just quickly mention a few other facts. Preservation of the number of solutions to equations, like this kind of equation, x to the k equals a, is going to have the same number of solutions as, maybe I should call it y to the k, as y to the k equals phi of a does. This is going to have the same number of solutions in G as this equation, where x and y are unknowns, does in G bar. And also, this might be a bit harder to prove, isomorphisms preserve the number of elements of various orders. So for example, S4 or S5 we saw today had how many elements of order 2? 5 times 4 divided by 2, is that right? And that was, oh no, that was only the 2 cycles, 10 of those. I think we had 15 that were compositions of disjoint 2 cycles, 25 total elements of order 2. Any group isomorphic class of 5 is also going to have 25 elements of order 2. We're about to go on to something more difficult here now. Properties of isomorphisms acting on groups. And for sake of time, I'm only going to maybe prove one of these properties, maybe the first one. Because I do want to mention a few other things and still get you out a little early. So we just looked at properties of isomorphisms acting on elements. What are properties of isomorphisms acting on groups? Here's the one I want to prove. Or at least think about the proof of. The inverse of an isomorphism is also an isomorphism. Which, by the way, verifies the symmetric property of isomorphisms. If G is isomorphic to H, then H is isomorphic to G. Isomorphism is an equivalence relation. Suppose phi from G to G bar is an isomorphism. Y is the inverse function, which definitely does exist. Because from chapter 0, since phi is 1 to 1 and onto, its inverse function will exist. Also an isomorphism. Phi inverse definitely will exist as a function because phi is 1 to 1 and onto. And in fact, because phi is 1 to 1 and onto, it's pretty easy to prove phi inverse is also 1 to 1 and onto. I forgot if in that problem you had back in chapter 0 if you fully proved that. I don't think you proved the inverse function was 1 to 1 and onto. I think you just proved it existed and satisfied these kinds of equations. Let's just prove the operation preserving part. When I apply phi inverse to the product of two arbitrary elements of G bar, call them G1 bar and G2 bar, do I get the same thing as when I apply phi inverse to G1 bar and also multiply that by what I get when I apply phi inverse to G2 bar? Are these the same? If you sit here and try to think about how to imagine showing those are the same, I think if you don't have the right intuition, you'll be stuck for a while. You're like, I have no idea what to do here. Here's one key thing to think about. The fact that phi itself is operation preserving must be relevant. So then the question is how you use the fact that phi itself is operation preserving, and then go ahead and experiment. Get some scratch paper out. Don't just start writing a proof on your piece of paper you're going to turn in. Have some scratch paper handy, or at least a board handy. And just try things. I do see a product of two things here that are in G. That makes me want to try applying phi to that product and use the fact that phi is operation preserving and see what I get. Phi is operation preserving. Use that. And that means that I would get this product. Lots of parentheses, it's very easy to make a mistake. Right? Since phi is operation preserving. You stare at this for a while and you suddenly realize, hopefully, that this is the same as G1 bar times G2 bar. Because phi and phi inverse are inverse functions, these equations. What happens when I apply phi to this? Use the fact that phi and phi inverse are inverse functions right away. This is G1 bar times G2 bar. I get the same image for these two things when I apply phi. Is that enough? Are we done? Does that mean phi inverse is operation preserving? Yes, but you should say one more reason. What's the one other reason besides the fact that those are the same that allows us to conclude that this equals this? There's one more fact you need.
Because phi is 1 to 1.
Because phi is 1 to 1, yep. Phi applied to these two inputs give the same outputs, the same images. Phi is 1 to 1, therefore the inputs must be the same. But now I use the fact that phi itself is also 1 to 1 to say that what I've underlined, those two things are equal. And that would verify phi inverse is operation preserved. I'm not going to prove these other facts today. Maybe one or two of them next Monday. If G is abelian, well, G is abelian if and only if its image under phi, which is G bar, is also abelian. So when I write that, I'm imagining I'm in the situation here that I've got an isomorphism between G and G bar, or from G to G bar. G is abelian if and only if G bar is abelian when you've got this isomorphism. They share the property of being abelian or not. If G is not abelian, then G bar will not be abelian. G is cyclic if and only if G bar is cyclic. And if G is not cyclic, then G bar will be not cyclic as well. G is not cyclic if and only if its image is not cyclic. You can negate both sides of an if and only if, and you get another true statement. The image of a subgroup of G is a subgroup of the image of G. Symbolically, what you're saying there is K being a subgroup of G implies phi of K is a subgroup of G bar, where phi of K is the image of K under phi is the sum of all outputs of phi where the inputs range over K. Set of all outputs of phi, phi applied to little k, where little k ranges over capital K. How would you prove it? You could use the one or two step subgroup test. It's a little tricky, but it's doable. It's not too bad. All of these proofs that I'm talking about today are exam level proofs. They could certainly show up on exam too. Here's something similar but a little trickier, at least in how it's described. The preimage of a subgroup of the image is a subgroup of the original group. What's a preimage? This is saying if K bar is a subgroup of G bar, it's got something called a preimage in G, which you can write this way. And that's going to be a subgroup of G. What is this thing? You can think of it in two ways. Since phi is an isomorphism, it's 1 to 1 and on to, it's got an inverse function, which we've just seen is also an isomorphism, just mentioned. You could think of this as the direct image of K bar under phi inverse. If you imagine these groups as being blobs, here's G bar, phi goes this way. In this last statement I'm just talking about, K is a subgroup of G. It's also a subset. Phi inverse goes back the other direction. You could think of this thing, phi inverse of K, since phi inverse does exist, as being the direct image, the set of all outputs of phi inverse when you let the inputs range over K bar. But it's going to turn out to be useful for us to think of this in another way, as what's called the preimage of K bar under phi, not phi inverse, as the set of everything in G that gets mapped into K bar. And that's going to be a useful way to think of it, because we will still think about this idea even in the context where maybe we have a function from G to G bar that's operation preserving, but not one-to-one and onto necessarily. And we will think about such functions in chapter 9. They're not called isomorphisms anymore, they're called homomorphisms. They're operation preserving, but not necessarily one-to-one and not necessarily onto. This idea will still be true in that context, but phi inverse no longer exists as a function. We can still talk about the set of elements in G that get mapped into K bar, though, in such a situation, and this property of being a subgroup will still be true. The image of the center of G is the center of the image of G. Phi of Z of G is Z of G bar. A couple more minutes here. Get off 5 minutes early. Okay? You should continue reading and thinking about these things and even trying to prove them on your own. You should also make sure you read before next Monday about aut G and in G, the group of automorphisms of G and the group of inner automorphisms of G. Maybe you've already read about those already. You should have. It's not an easy subject, but is definitely something we want to think about some. Okay, it's helpful in some circumstances when you're studying groups to think about automorphisms with the group and these special automorphisms called inner automorphisms. Let me end by just giving you a preview of the most important theorem in group theory, which is the main subject of chapter 7. It's called Lagrange's theorem, called the cornerstone of group theory. You could also call it also known as the fundamental theorem of group theory. Okay? And in its most simple form, you could just state it like this. If G is a finite group and H is a subgroup of G, then the order of H divides the order of G. Now, we already knew this was true for cyclic groups. The order of a subgroup must divide the order of a group. For example, if the order of the group is 20, then the possible orders of subgroups would be the divisors of 20, which would be 1, 2, 4, 5, 10, and 20. I'm missing today. 6 of them. Doesn't guarantee that there are subgroups of each order that divides 20, but if H is a subgroup of a group of order 20, it's got to have order 1, 2, 4, 5, 10, or 20. It's got to divide the order of the entire group. That's true even for non-cyclic groups. That is Lagrange's theorem in its simplest form. You can say a little bit more, but it involves some new terminology. You can say the number of left cosets and right cosets is the quotient, order of G divided by the order of H. Now, I haven't said what a left coset is. I haven't said what a right coset is. In your reading, which you should do in chapter 7 for next Monday, you will learn what left and right cosets are. A couple quick corollaries that are pretty interesting to think about. in a finite group, the order of each element must divide the order of the entire group, because each element is going to generate a cyclic subgroup whose order is the same as the order of the element. Another corollary that's much harder to prove, is proved in the book and is labeled as a theorem, is pretty interesting. If P is a prime greater than 2 and G is a group of order 2P, then there's only two possible things that G could be, so to speak. Two groups it could be isomorphic to. Either Z2P, cyclic group of order 2P, or DP, the dihedral group of order 2P, symmetries of a regular p-gon, including both rotations and reflections. It's got to be isomorphic to one of those two things. So any group of order 6 is isomorphic to Z6 or D3. Any group of order 10, 2 times 5, is isomorphic to either Z10 or D5. Any group of order 14, 2 times 7, is going to be isomorphic to either Z14 or D7. That's pretty astounding that you could say such a thing. Any group of order, what would it be? Maybe like 82, which is 2 times 41. 41's prime is isomorphic to either Z82 or D41. That's a pretty strong corollary, and again, the book calls it a theorem, chapter 7, because it's a pretty profound fact. It's harder to prove, but part of the proof does involve using Lagrange's theorem. So you can think of it as a corollary of Lagrange's theorem. All right, see you Monday.